The next speaker, Sichen Jean. I hope that I pronounce her name correctly. And her talk will be on real-world deployment of end-to-end speech recognition. So Sichen Jean, she is, let me just a little bit give a brief bio of her. She's a data scientist or engineer at Samsung R&D from Korea. Sichen is a research engineer in the speech processing lab at Samsung Research. Her work include implementing and training models of latest trend, mainly in automatic speech recognition area, as well as finding new optimal models. Sichen is curious about various deep learning network models and techniques to get the best performance out of them in different area of machine learning. Sichen is experienced at training both extremely small and large model, as well as embedding them in different devices for commercial use. Prior to joining Samsung in Korea, Sichen received her bachelor in computer science engineering from Seoul National University. So I would like to open the floor to her so that we can learn from her experience, and the question will be at the end of the session. Welcome. I would like to welcome Sichen. Go ahead.
Hello everyone. I hope my video, my display is being shared now. Hello everyone. My name is Sichen Jin, and I work as a research engineer at Samsung Research, Korea. First, I want to say that it's a great honor to give a speech at such a meaningful event, and I hope you enjoy my speech. So in today's talk, I will first introduce what ASR is and show you a widely used neural network-based model in this field. And then I will tell you about some of the difficulties we had deploying the technique into real products and introducing it to our real users. And finally, since I'm at a Women in Data Science event, I will briefly talk about my experience learning and working in this field. So what is ASR? I'm sure most of you are already familiar with these products shown in the slide, and most of you may already be using them on a daily basis. Over the past few years, voice assistants have become viral and immersed into everyone's life, and they can be found not only on smart speakers or our phones, but also on cars, TVs, high-end refrigerators, and any electronic devices imaginable. And ASR, we can say, is the ear of a voice assistant. An ASR model takes a sequence of speech in audio form as the input and outputs a sequence of words as the prediction for the content of the speech. Besides voice assistants, ASR can also be used as a keyboard input method or for the automatic caption generation function on YouTube that you're using. And with the use of neural networks, the ASR models are becoming smaller and more efficient, which enables us to exploit the technique in even more areas. Now, let me take you through how an ASR model generates predictions for input speeches. It was shown a long time ago that speech signals have a stationary interval of 20 to 30 milliseconds. So we don't process the whole raw speech audio at once, but take only 30 milliseconds of the speech and process them into a feature vector to feed them into the neural network. So given an input speech in audio form, we take a sliding window of size 30 milliseconds and move it along the time axis with stride of 10 milliseconds to process input speech into feature vectors. So now we have the input feature vectors coming in every 10 milliseconds. And for the output, we can choose between different levels of representations for written form. For example, on the slide, we can choose to use word level representation and let the model generate high and Bixby 2 words as the output. Or we can choose to use the character level representation and let the model generate HI space BIXBY, so 8 characters. Then now it's not hard to see that the most challenging part for making a neural network-based ASR system is the huge difference between the number of the input features and the number of the output tokens. So in 1 second speech, high Bixby, we can have around 100 input features, whereas there are just 2 output tokens if we use word level representation, or 8 of them if we use character level representation. So we want to make the neural network itself learn the alignment between the input features and output tokens. Now let me introduce the most widely used neural network model for streaming ASR, a transducer model. The model has an encoder network to process the input features, a prediction network to process the previously predicted tokens, and a joint network to predict the next token. At first, an input feature is consumed, and the same hidden state HT_INC is used until a blank symbol is predicted from the model, meaning there is no more prediction can be done for this input feature. And meanwhile, whenever there is a non-blank vocabulary predicted from the model, it is fed into the prediction network to make hidden state PU. And the joint network runs when there is a new hidden state from either the prediction network or the encoder network and gives us a new distribution of for output tokens. I know you must be very confused by my explanation, so let me show you an example. Say we have 4 input frames for x-axis, and we want to predict the word cat in character level, so CAT for y-axis. Please follow the red arrows on the graph. So starting from the bottom left, we make a new hidden state HINC1 by consuming 1 input feature with the encoder network, and then a new hidden state P0 by consuming a beginning of sentence symbol with prediction network as the start of the sentence. And these hidden states go through the joint network and the softmax layer to make the output distribution for the first output. And the arrow goes upward, so it means the first label C has the highest score among the vocabularies. Now that we have a non-blank output, we feed it back to the prediction network and get a new P1, and it's fed into the joint network with the unchanged HINC1, and the arrow goes up again, which means the next token A is also predicted from the same frame. Now, just as what was done before, A is fed back again into the prediction network, and a new P2 goes into the joint network with unchanged HINC1. And finally, the arrow goes to the right, which means the blank symbol got the highest score among the vocabularies. And the model knows the input feature at this time step is done. So we consume another input feature and feed it with the unchanged P2 into the joint network. And the inference goes on like this. I hope I explained it. So the probability of each path is computed as the production of the probabilities of each token along the path, which is the softmax output of the model. And the probability of the target sequence is computed by summing over all possible alignments, which we aim to maximize during training. This model is almost the standard model structure nowadays, with some changes in the details of subnetworks. Like we can choose to use LSTM or attention-based network for the encoder, or we can use some different networks for the prediction network again as well. And most importantly, it's what we use at Samsung for our own on-device products. So we've decided to use so we've decided that we will use RNT structures for commercialization, and we trained the model, and we are very confident. But once it's out in the market, people start to complain that it's too slow, it's not accurate, blah, blah, blah. So we have to make some changes to the model to better satisfy our customers. And now I will introduce some of the techniques we use for deploying the neural network-based ASR onto our phones. So more and more people are aware of privacy issues in today's information world. Information leaks and unauthorized use of information are the main threats people are facing. And how comforting will it be if we can do the whole speech recognition process on the phone without sending any information to the server? We've been working on-device speech recognition for the last few years, and it has the advantage in terms of privacy, recognition speed, and is totally free from network restrictions. It was advertised at the recent Galaxy Unpack event for new Samsung phones that our model could achieve 35% faster in speed thanks to doing speech recognition fully on device. So neural network-based ASR models were smaller compared to the conventional statistical ASR models, but they were not small enough to run fully on device. And smaller models mean faster inference speed, so we had to reduce the model size. And the first technique we tried was called SVD compression, which is also called low rank approximation. Say we have part of a neural network that looks like this on slide, and it's a stack of dense layers and activation layers. A dense layer does nothing more than multiplying a matrix A to the input vector, and we aim to split the big matrix A into two smaller matrices B and C without losing much of its information. So we are splitting a matrix of n times d into two matrices, n times r and r times d. And we are doing this to reduce the model size. So we need the r to be smaller than n times d over n plus d, which is roughly half of n if we assume n and d are in this same scale. And if d is twice n, like the example on the slide, r should be smaller than 2/3 of n. So how we do this is we perform singular value decomposition on matrix A and get a matrix U of n times n, a diagonal matrix sigma of n times d, and a matrix V transpose of size d times d. And if you are familiar with linear algebra, you will know that sigma contains the singular values of A. So with sigma in decreasing order, we take the top R singular values, which means we are taking the top R vectors from U and V transposed as well. So the pink parts on the slide are kept, and we recompose them into two matrices, U hat times sigma hat as matrix B, and V hat transpose as matrix C. So SVD compression is actually also used in image compression, and I think you will be able to get the gist of it if you take a look at the compressed images. The K on this slide is the R on the previous slide, and you can see that with D decreasing, although the edges are not as sharp as before, we can still recognize that the picture is one of Einstein's. And when the rank is half the original rank, which we aim to make, and here, which is the picture E, the picture still seems pretty good. So the whole compression process goes like this. Before compression, we train a normal model until it converges into its full accuracy. Then weight distortion is done in an occasional manner. Here, weight distortion means performing SVD decomposition on a target matrix A and remaining only the top R singular values and recomposing the matrices into the same sized A with reduced rank and assign the variable to the original matrix A. So the training algorithm itself doesn't need to change, and the additional computation caused by weight distortion is also neglectable. As the training for the compression goes on, the accuracy drop through a weight distortion step decreases. In other words, the loss function degradation caused by a weight distortion is gradually diminished. As you can see in the training curve, the final loss recovers to the original loss at the beginning of the compression, so before compression. And we end the training right after the weights are distorted to hold the compression format of the weights. So with this compression method, we were able to reduce the model size from over 500 megabytes into 140 megabytes with little or no degradation at performance. And we could do the whole inference in almost 20% of the time it used to take. As appealing as the result is, the method worked very well on attention-based models, but it suffered when we tried to compress an LSTM-based model with it. So we had to try a second compression method, knowledge distillation. So it's a method for transferring the knowledge of a big model to a smaller model. We combine the KL divergence score between the logics of the teacher model and the student model and the loss of the student model to form the objective function. And this helps to train the student model to learn the task in the probability distribution of the teacher model. And the point of this is that when we train neural network models, we often use regularization methods to prevent the models from overfitting. And the teacher model is likely an ensemble of several smaller models from regularization skills, such as dropout. And when a student model learns the output distribution of the teacher model, we expect the student model to capture the average of the variables in the ensemble models in the teacher model. And if we train a smaller model from scratch with the same generalization methods, we will end up with an ensemble of even smaller models. So it can never beat the student model trained with knowledge distillation. And with knowledge distillation, we could achieve a 55% reduction on model size with very little degradation of at performance. And the second column in the table shows a model of the same size as the student model trained from scratch without knowledge distillation. And you can see the performance is not as good as the student model that was trained with knowledge distillation. And the next challenge for deploying ASR into our product was personalization. Say you want to ask Bixby to call Emily with IE in the end for you, but then you don't want the model to always predict call Emily with Y in the end, just because it has more occurrences in our training data, and because it's what neural networks do. So we need a method to bias the ASR model to produce Emily with IE in the end more. So a language model is a model that predicts the next word given the previous words. So if you feed how and are in the model, it predicts the probability distribution of the next word, which is very likely to be you, or it can also be these or they. And a simple skill called shallow fusion enables us to use the language model to help ASR models. In this method, we simply add the softmax score produced by the ASR model and the language model in log scale with a weight lambda. Despite the simplicity, the technique works very well for combining the ASR results and the result from external language models. But don't forget that the language information we are going to use are from the user's phones, such as contact lists, song title lists, or IoT device names. And we need to make a language model on the fly on the phone, which means we cannot train a neural network language model for this purpose. So we actually went back to the statistical models to do it. Statistical models are easier to make than to train a neural network on the phone. So building an n-gram model is actually very simple. We just simply need to count the occurrences of each combinations of words. So from the previous example, given how R and to predict the probability of the next word being U, we divide the number of how R U's found in the training data by the number of how R's found in the training data, because that's the conditional probability of the target. But we can't always believe that the training data contains all possible combinations of vocabularies. What if somehow there was no how are you in the training data? With this naive way, all the probabilities of unseen combinations will become zero, which is very dangerous, and that's why we use some of the smoothing techniques. So in plain words, smoothing techniques try to take some probabilities from the existing combinations in the training data and distributes them to unseen combinations of words. There are a lot of complicated and sophisticated smoothing methods, but here I will just introduce the simplest smoothing technique, just as an example, called add-one smoothing or Laplace smoothing, where we simply add 1 to all the counts of all possible combinations. And this way, even unseen combinations will not get 0 as a probability. In individual phones, we gather the language information from the user's contact lists, music playlists, and IoT device lists, etc., and make n-gram language models with them, and perform shallow fusion when we run ASR models. With n-gram biasing, we could achieve better performances in individual domains without destroying the general ASR performance. But language models only bias the ASR model. They don't ensure that recognition results are in the target named entity lists. So we further restrict the named entities with a named entity correction module that happens after the ASR model has produced its hypothesis for the speech. Say the ASR model gave a hypothesis, play Charlie put. As humans, obviously, we know the correct prediction should be play Charlie put. And now let's see what the named entity correction module does to find out the correct answer. So first we have a keyword-based domain classifier, which declares that the sentence is from music domain from the keyword play. And then we use a named entity extractor to extract the name from the sentence by comparing the sentence with some prepared raw files. After the name is extracted from the hypothesis, we compared the name with the target list and find the closest one to return as our final output. First, we compute the word level edit distance between the hypothesis and the singer and all the singer names in the list. And we have a threshold for the score above which we will keep them into the next level of matching. And here, 3 candidates are chosen: Charlie Booth, Charlie Puth, and Charlie Wilson. Next, we compute phonetic level edit distance. And again, we use a threshold to decide which candidates we are going to keep. Here, since Charlie Booth and Charlie Puth, both of them sound very much like Charlie Puth. So it's likely that they are kept for the last level of matching. And finally, we have a grapheme level matching, which is character level matching. And since Charlie Puth is closer to the original hypothesis Charlie Puth, we choose this Charlie Puth as the final output and replace the original hypothesis with this. This method may look really naive, but it was quite powerful. And again, we were able to achieve better performances in individual domains without destroying the general ASR performance. So these were the techniques we used to provide better user experience for our customers, and it leads us to the last bit of my speech, my personal experience studying and working in data science. So preparing this part, I really wanted to depict a touching story of struggling and striving, but unfortunately, or should I say fortunately, I didn't have a lot of crisis during my school years or working days. Yes, I did grow up in an environment where people believed boys are better at STEM subjects than girls. And I was always the minority in my math class or my science classes and at work. But I liked learning STEM subjects, and the majority in my class or at work didn't treat me too differently just because I am a woman. At the end of the day, we are not that different at all. Some girls may like science more, and some boys may like liberal arts more, and who you are doesn't really matter, I think. But I do feel really lucky to have studied and worked in this kind of environment, and I hope other women can feel this too. So I really appreciate this event, and I look forward to hearing from other women from other cultures. And for the last bit of my speech, I want to make a small advertisement for our product, Bixby. So you can find the server-side Bixby or on-device Bixby on Samsung phones by calling Hi Bixby or trying out the voice input function in the keyboard. So thank you for listening to my speech, and now I will take some questions.
Thank you, Sichen. It was really,
Yeah.
I mean, the talk was very, very nice and stimulating, but thank you very much for the end, the last message, because I was thinking about saying something since it's a workshop for women in data science. So I wanted to just not listen to talks, but deliver a message for young scientists who are female. And your message has come to the right point. So it means that we should not be scared about choosing IT, technology, computer science, mathematics. We need to have the courage to get into it. And you are a perfect example for that. Thank you so much. Thank you. That was really
Yes, exactly. We just need to do what we like, and yeah, that's all.
And sometimes, as you said, there is also some kind of cultural barrier about that. So we are familiar about the fact that probably in a family, even though if the girl is very good in math, we have the tendency to probably send her to something like maybe management or medical, and the boy will go to IT, etc. So this is you are a
Yes.
perfect example of that. So we can always bridge that gap. So so while waiting for so I have a couple of questions here. That's a great presentation,
Yeah.
actually. So one of the questions that I received is, can you please provide some insight on what would be the effect of switching between language in Korean or having accented speech in the ASR output and performance? And how can it be handled for a robust in the wild ASR?
Uh, Sorry, can I listen to the question again?
Okay, so can you
Yeah.
please provide us with some insight on what would be the effect of switching between languages? For example, English to Korean, Korean to English. or having a sentence speech in the model that you just explained? Is it something easy to handle? So it means like when you are having like we know that there is a gap, I think, multilingual gap. So how can the ASR model handle that?
So we are doing some researches on multilingual ASRs. So as I mentioned during the speech, we have output tokens for each languages. So for Korean, for English, we have characters or words. For Koreans, we have like Korean graphemes or Korean words. We use different output tokens as the output and train different models. But for multilingual ASR models, we have to somehow unite the output tokens and make the model generate these tokens. And there are some researches done in this area, and they use byte like UTF-8 encoding byte as output tokens, and they train the models with those output tokens. And I think, yeah, those output tokens can use, with those output tokens, we can use one model to do speech recognition, with both the languages. Yeah.
Another question quickly, because we have only 1 minute. What would you suggest to
Okay.
the young people who want to pursue and learn more about space technology? So what will be your advice to the young scientists?
My advice is just go for it, and like there is nothing to be scared about. You just need to try, and it will work. Yeah, as long as you believe in it. Yeah.
Yeah.
Thank
So
you.
is there any other question? I think there is one. I can take the risk to ask you this because we still have 1 minute.
Yeah.
What is the intuition behind using word level matching before the phone-based approach? So what is the intuition?
Yeah, actually, that is a really good question. So for us, the reality is sometimes we can have like very many named entities in the named entity target list, and some of them are like even phrases. So some of them are not just words like Charlie Puth. Some of the like song titles may be like sentences or phrases. So we had to first reduce the number of named entities so that we won't like waste too much time for when we do like grapheme level matching or character level matching. So actually we didn't really do word level matching before the phonetic matching and character level matching. The reason why we added the word level matching is because we wanted to like reduce the named entity list for size of the named entity list first. Yeah, so that's the answer.
And quickly, because someone was insisting on asking this question, so I will not skip it. So, using on the device ASR, is the model adapted to user speaking style and voice?
No, actually, because neural network models are really difficult to be trained on device. So the most like the simplest bias we can do is the language model biasing. But I think with like the NPUs and GPUs are going into the phones, we can try like training our model on device with the like data we collect from the users. So I think that's the way that we can go for.
So thank you, Sichen. It was really very stimulating and nice talk. I would like to, applaud you with also the help of the audience. So thank you very much, and hope we will see you at the panel. Thank you.
Thank you for having me. Bye-bye. Yeah.
So much. Bye. So our next speaker, since we are 1 minute.